October 12th, 1954, USS Forrestal, 200 miles northeast of Norfolk, Virginia. Salt spray whips across the flight deck as Lieutenant Commander Dennis Walsh grips the controls of his F9F Panther, lined up for what every naval aviator knows is the most dangerous moment in military aviation: carrier landing. The deck pitches violently in 12-foot swells while a 20-knot crosswind tries to push his aircraft into the churning Atlantic. Behind him, 14 more jets circle in the landing pattern, fuel gauges dropping toward emergency reserves as pilots wait their turn to attempt what kills more Navy flyers than enemy action. Walsh has logged 847 carrier landings without incident, but statistics offer cold comfort when every approach could be his last. The numbers are brutal and unforgiving. 1 in every 12 carrier landings results in a crash, twisted metal, fire, and young pilots who will never see their 25th birthday. The Navy's best aviators are dying at a rate that makes combat operations look safe by comparison. But Walsh isn't thinking about statistics as he calls the ball, confirming visual contact with the optical landing system that will guide him home. He's thinking about an idea that every flight instructor has dismissed as fundamentally wrong. A landing technique so radical that seasoned pilots laugh when he describes it. An approach method that violates every principle of naval aviation that has been taught since carriers first went to sea. Yet the mathematics in his logbook suggest something extraordinary. In 63 landings using his unorthodox technique, Walsh has achieved perfect success rates while pilots around him continue auguring into steel decks with depressing regularity. Tonight he's about to demonstrate his impossible landing method to a collection of senior officers who expect this experiment to end in spectacular failure. The genesis of Walsh's revolutionary approach began 8 months earlier in the ready room of VF-21, where Lieutenant Junior Grade Bobby Martinez was explaining why he'd never fly again. The 22-year-old from East Los Angeles sat with his left arm in a cast, his face bearing the kind of 1,000-yard stare that came from surviving what most pilots didn't. His F4U Corsair had caught a wire wrong during a night landing, snapping the aircraft sideways into the island superstructure at 90 miles per hour. The impact had crushed his shoulder and filled the cockpit with jet fuel that somehow never ignited. Martinez was lucky to be breathing, much less talking about the accident that ended his naval aviation career. Walsh listened to the accident report with the methodical attention of someone who understood that every crash contained lessons for pilots smart enough to learn from other people's mistakes. Approach speed 140 knots, exactly by the book. Angle of attack precisely as specified in the flight manual. Power setting maintained according to standard operating procedures. Everything had been textbook perfect until physics and steel deck reality intervened with mathematical certainty that left twisted aluminum where a fighter aircraft used to be. The investigation board had ruled pilot error, citing insufficient power management during the final approach phase. But Walsh saw something different in the wreckage patterns and witness statements. The accident wasn't caused by what Martinez had done wrong. It was caused by what every naval aviator had been taught to do right. Traditional carrier landing doctrine emphasized consistency above all else. Maintain precise airspeed, hold exact glide slope, keep power settings steady throughout the approach. Naval Flight Training Command had developed these procedures through decades of operational experience, refining techniques that transformed civilian pilots into carrier-qualified aviators, capable of landing on moving decks in conditions that would ground commercial aviation indefinitely. The system worked adequately most of the time, producing pilots who could execute acceptable landings under normal conditions. But normal conditions didn't exist in naval aviation. Carrier decks moved constantly through 3 dimensions as ships rode ocean swells that could lift or drop the landing area 20 feet in seconds. Crosswinds created approach angles that changed continuously as aircraft descended toward decks that might not be where pilots expected when they arrived. Most critically, the traditional approach method left pilots with limited options when conditions deteriorated beyond standard parameters. Fixed airspeeds and rigid power settings worked perfectly in calm seas with steady winds. They became death traps when weather or mechanical problems demanded instantaneous adjustments that standard procedures couldn't accommodate. Walsh had noticed patterns in accident reports that suggested fundamental problems with conventional landing techniques rather than individual pilot failures. Crashes occurred most frequently during approaches where pilots attempted to maintain textbook parameters despite changing conditions. Aircraft that flew perfect approaches according to flight manual specifications ended up in barriers or over the side because rigid adherence to procedures prevented adaptive responses to dynamic situations. The mathematics were disturbing when analysed systematically. 68% of carrier landing accidents involved aircraft that were following standard operating procedures correctly until impact. Pilots weren't failing because they ignored their training. They were dying because their training ignored the reality of how physics worked when metal met moving deck under less than ideal conditions. The breakthrough insight came during Walsh's study of aerodynamic theory at the Navy's Test Pilot School, where advanced mathematics revealed relationships between angle of attack, power settings, and aircraft response that weren't addressed in standard flight training curricula. Traditional landing approaches treated airspeed as the primary variable to control, with power adjustments used to maintain desired descent rates. But Walsh's calculations suggested that this relationship was backwards for carrier operations. Power should be the primary control input, with airspeed allowed to vary within acceptable limits based on conditions. The distinctions seemed minor in classroom discussions, but it represented a fundamental shift in how pilots thought about controlling their aircraft during the most critical phase of flight. Instead of flying the airplane to maintain specific numbers, pilots should fly the airplane to maintain optimal energy states that could adapt to changing conditions. Commander Jake Thompson, the Air Group's most experienced landing signal officer, initially dismissed Walsh's theory as academic speculation from someone who spent too much time with slide rules and not enough time in actual cockpits. Thompson had guided over 4,000 successful carrier recoveries using traditional techniques, and his experience provided credibility that theoretical calculations couldn't match. 30 years of naval aviation had taught him that innovation usually meant inexperienced pilots trying to reinvent procedures that had been perfected through thousands of hours of operational testing. The system worked because it had been proven under every conceivable condition by aviators, whose lives depended on getting it right. Young pilots with engineering degrees and revolutionary theories typically ended up as smoking holes in flight decks when they tried to improve techniques that didn't need improvement. But Walsh possessed the quiet persistence of someone who had learned to trust mathematics over conventional wisdom. His engineering background from MIT provided analytical tools that revealed patterns in accident data that operational experience might miss. Every crashed aircraft told a story about the interaction between pilot inputs, aircraft response, and environmental conditions. When those stories were analysed systematically rather than individually, they revealed consistent themes about why traditional approaches failed under specific circumstances. The failures weren't random events caused by pilot error or mechanical problems. They were predictable consequences of using fixed procedures in dynamic environments that demanded adaptive responses. The first unauthorized test of Walsh's modified landing technique occurred during a routine training flight on February 18, 1954. Weather conditions were marginal but acceptable, with 15-knot winds and 3-foot seas that created deck motion within normal parameters. Walsh had requested permission to demonstrate his approach method, but Thompson had denied the request pending further review by squadron leadership. Flying his assigned training profile, Walsh broke from the pattern at the last moment and executed his revolutionary approach under conditions where failure would result in immediate grounding and possible court-martial proceedings. His technique violated every principle of standard carrier landing doctrine while achieving results that challenged fundamental assumptions about what constituted proper flying. Instead of maintaining constant airspeed through traditional power management, Walsh allowed his Panther to accelerate and decelerate naturally, as he adjusted power settings to control his descent path directly. The approach looked chaotic to observers who expected the mechanical precision of textbook carrier landings. His airspeed varied by 15 knots throughout the approach, fluctuating between 125 and 140 knots as power changes created energy states that responded dynamically to deck motion and wind shifts. But the aircraft's flight path remained remarkably stable, tracking the glide slope with corrections that seemed to anticipate deck movement rather than react to it. Thompson watched from the landing signal officer platform with growing alarm as Walsh's Panther descended toward the deck in what appeared to be a completely uncontrolled approach. The aircraft's speed variations violated every safety protocol that 3 decades of carrier operations had established. Standard procedures existed precisely to prevent the kind of erratic flight behavior that Walsh was demonstrating with apparent deliberation. Yet something about the approach felt different from the unstable approaches that typically preceded crashes. Despite the speed variations, the aircraft maintained precise lineup and glide path control that suggested intentional technique rather than pilot incompetence. The touchdown occurred with mechanical authority that surprised everyone observing the evolution. Walsh's main landing gear contacted the deck exactly at the intended touchdown point, engaging the number 3 wire with perfect centering that indicated precise spatial awareness throughout the approach. The aircraft decelerated smoothly as the arresting gear absorbed kinetic energy, bringing the Panther to a controlled stop without the violent deceleration that often accompanied carrier landings. Most significantly, the landing had been accomplished without the last-second power corrections that characterized most successful carrier recoveries, suggesting that Walsh's technique had maintained optimal energy states throughout the approach rather than requiring emergency adjustments at the critical moment. Thompson's radio crackled with Walsh's voice as the pilot taxied clear of the landing area, his tone carrying the satisfaction of someone who had just proven a controversial theory under operational conditions. "Power approach technique successful," he reported, understanding that his unauthorized demonstration would generate significant discussion among squadron leadership, who had specifically prohibited experimental landing methods. The technique maintains energy control throughout approach phase, rather than requiring speed corrections during final segments. The mathematical elegance of Walsh's approach became apparent during post-flight analysis, as squadron engineers examined telemetry data that documented every aspect of the landing evolution. Traditional approaches showed characteristic patterns of power adjustments clustered around the final approach phase, where pilots struggled to maintain precise parameters as deck motion and atmospheric conditions changed rapidly. Walsh's data revealed a fundamentally different pattern, with power changes distributed throughout the approach in a way that anticipated environmental variations rather than reacting to them. The technique treated the aircraft as an energy management system rather than a speed control problem, allowing natural aerodynamic relationships to provide stability instead of fighting against them. Lieutenant Commander Sarah Chen, the squadron's senior engineering officer, spent 3 days analysing Walsh's flight data before reaching conclusions that challenged her own understanding of carrier landing dynamics. Her background in aeronautical engineering from Cal Tech provided mathematical tools needed to quantify what observers had witnessed qualitatively. Energy state management appears to provide superior approach stability compared to traditional airspeed control methods, she wrote in her preliminary analysis. Variable speed technique maintains more consistent glide path control while reducing pilot workload during critical approach phases. The implications extended beyond individual landing technique into broader questions about how naval aviation training prepared pilots for carrier operations. If Walsh's method provided measurably superior results, why had decades of operational experience failed to discover these advantages? The answer lay in institutional resistance to change that characterized military organizations, where proven procedures carried the weight of tradition and safety records. Standard techniques worked adequately for most pilots under most conditions, creating institutional momentum that discouraged experimentation with methods that might offer improvement, but carried risks of catastrophic failure during development phases. Commander Robert Hayes, commanding officer of VF-21, found himself facing a decision that could affect his career and potentially revolutionize naval aviation training. Walsh's unauthorized demonstration had violated direct orders, warranting disciplinary action that would normally result in grounding and fitness for duty evaluation. But the technical results suggested potential improvements in safety and operational effectiveness that demanded serious consideration despite irregular circumstances. Military leadership required balancing adherence to established procedures against recognition of innovations that might enhance mission capability through improved techniques. The squadron's safety record provided compelling context for evaluating Walsh's claims about landing technique effectiveness. VF-21 had experienced 4 carrier landing accidents in the previous 8 months, resulting in 2 fatalities and significant aircraft losses that affected operational readiness. Each accident had involved experienced pilots following standard procedures correctly until environmental factors overwhelmed their ability to maintain approach parameters within acceptable limits. The crashes weren't caused by training deficiencies or pilot error in the conventional sense. They resulted from systematic limitations in traditional landing techniques when applied under marginal conditions that exceeded design assumptions. Hayes authorized controlled testing of Walsh's modified approach under carefully supervised conditions that would provide data needed to evaluate safety and effectiveness claims. The test protocol required experienced pilots to demonstrate both traditional and modified techniques under identical conditions, creating direct comparisons that would reveal actual performance differences rather than theoretical advantages. Most importantly, testing would occur during daylight hours with optimal weather conditions, eliminating variables that might mask fundamental technique differences or create unnecessary hazards during evaluation phases. The first official test occurred on March 2, 1954, with Lieutenant Commander Mike Rodriguez executing both approach methods in consecutive landings aboard USS Randolph, operating in calm seas with minimal wind conditions. Rodriguez possessed over 600 carrier landings in his logbook, providing experience necessary to evaluate technique differences without introducing pilot proficiency variables that might contaminate test results. His reputation for precise flying and analytical thinking made him ideal for documenting subjective pilot workload differences between conventional and modified approaches. Rodriguez's first approach used textbook technique, maintaining 135 knots throughout the pattern, with power adjustments limited to minor corrections needed to hold glide slope. The landing was successful by conventional standards, engaging the number 2 wire with acceptable deceleration characteristics. But his post-flight debrief revealed workload patterns that had become so routine he rarely noticed them. Constant speed control required continuous attention to airspeed indicators and power settings, creating mental workload that demanded focus on instrument monitoring rather than external visual cues about deck motion and approach geometry. The second approach implemented Walsh's power control technique, allowing airspeed to vary between 128 and 142 knots, as Rodriguez used throttle movements to control descent path directly. The sensation was initially uncomfortable for a pilot trained to maintain precise speeds, but the aircraft's response felt more natural as power changes created immediate flight path corrections without the lag time associated with traditional speed control methods. Most significantly, the technique freed Rodriguez to focus on visual references and deck motion rather than instrument monitoring, improving situational awareness during the critical final approach phase. The touchdown comparison revealed subtle but measurable differences that accumulated into significant operational advantages. Walsh's technique produced consistently shorter landing distances with reduced stress on arresting gear systems, suggesting more efficient energy management throughout the approach evolution. But the most important difference was pilot confidence and workload reduction that translated into better decision-making during marginal conditions, where split-second responses determined success or catastrophic failure. Lieutenant Commander Rodriguez filed his report that evening, his words carrying the weight of someone who had experienced a fundamental shift in understanding about how aircraft should be controlled during carrier approaches. The power control method feels counterintuitive initially, he wrote, but provides superior flight path management with reduced pilot workload during critical phases. Traditional speed control techniques now feel mechanically restrictive compared to the natural energy management that variable speed approaches allow. The technical analysis conducted by squadron engineers revealed performance differences that extended beyond subjective pilot impressions into quantifiable measurements of landing accuracy and safety margins. Walsh's technique consistently produced touchdown points within 50 feet of the optimal wire engagement zone, compared to traditional approaches that showed touchdown dispersions of nearly 200 feet under identical conditions. The improved precision translated directly into reduced wear on arresting gear systems and decreased probability of barrier engagements that damaged aircraft and endangered flight deck personnel. More significantly, the power control approach demonstrated superior performance characteristics during simulated emergency conditions where traditional techniques often proved inadequate. When test pilots attempted single-engine approaches using conventional methods, success rates dropped to 60% as reduced power authority made precise speed control nearly impossible. The same emergency scenarios using Walsh's technique achieved 95% success rates because power control methods adapted naturally to degraded aircraft performance without requiring fundamental changes in pilot technique or mental workload distribution. Commander Thompson reluctantly acknowledged that Walsh's approach method produced measurably superior results, despite violating every principle of landing technique that 30 years of experience had validated. The landing signal officer's credibility depended on maintaining safety standards that protected pilots from experimental techniques that might prove catastrophically inadequate under operational conditions. But the accumulated test data suggested that traditional methods might actually be less safe than the revolutionary approach that challenged institutional wisdom about proper carrier landing procedures. The resistance from Naval Flight Training Command was immediate and absolute when preliminary test results reached Pensacola headquarters. Captain William Morrison, Director of Carrier Landing Training, possessed unquestioned authority over techniques taught to student naval aviators throughout the training pipeline. His 25 years of instructional experience had established standardized procedures that produced competent carrier pilots through methodical progression from basic aircraft control to complex deck landing operations. Morrison viewed Walsh's technique as dangerous experimentation that threatened systematic training methods proven effective across thousands of successful pilot graduations. Experimental landing techniques represent unacceptable risks to student pilot safety, Morrison stated during a heated telephone conference with VF-21 leadership. Standard procedures exist because they have been validated through operational experience that costs lives when ignored. Individual pilots may achieve temporary success with unorthodox methods, but systematic training requires techniques that work consistently for average pilots under normal conditions, rather than exceptional techniques that depend on superior pilot skills. But Walsh possessed statistical evidence that challenged Morrison's fundamental assumptions about what constituted safe and effective landing techniques. His analysis of fleet accident reports revealed disturbing patterns that suggested traditional training methods were producing pilots who crashed at predictable rates because their techniques became inadequate when conditions exceeded narrow parameters. 63% of carrier landing fatalities involve pilots with more than 200 successful landings, suggesting that experience with standard techniques provided false confidence rather than improved safety margins under challenging conditions. The mathematical relationship between approach technique and accident probability became clear when Walsh analyzed landing data across multiple squadrons operating under identical conditions. Traditional approaches showed accident rates that increased exponentially as environmental conditions deteriorated beyond optimal parameters. Wind speeds above 15 knots, deck motion exceeding normal limits, or visibility restrictions created failure modes where standard techniques proved inadequate for maintaining safe approach control. Power control approaches maintained consistent safety margins across broader environmental envelopes, suggesting fundamental superiority in adaptability to changing conditions. Lieutenant Sarah Kim, a recent graduate from Naval Flight Training who had joined VF-21 2 months earlier, became Walsh's most valuable test subject because her limited experience with traditional techniques made her ideal for evaluating training effectiveness using modified approaches. Kim possessed excellent flying skills but lacked the ingrained habits that made experienced pilots resistant to technique modifications. Her progress using power control methods would reveal whether Walsh's approach required exceptional pilot abilities or could be taught systematically to average naval aviators. Kim's initial instruction in power control technique occurred in the squadron's flight simulator, where Walsh could demonstrate energy management principles without risking aircraft or personnel during the learning process. The simulator revealed immediate differences in how pilots thought about aircraft control when freed from rigid speed maintenance requirements. Instead of fighting to maintain precise numbers on instruments, Kim learned to feel aircraft energy states through control responses that provided intuitive feedback about flight path management and approach geometry. The transition to actual flight testing proceeded gradually as Kim mastered power control concepts under increasingly challenging conditions. Her first carrier qualification attempt using Walsh's technique occurred during ideal weather with minimal deck motion, providing optimal conditions for evaluating training effectiveness without introducing environmental variables that might complicate technique assessment. The approach felt natural despite violating every landing method she had learned during flight training, demonstrating that power control principles could be taught effectively to pilots without extensive experience using traditional techniques. Kim's successful qualification using exclusively power control methods provided compelling evidence that Walsh's approach could be integrated into systematic training programs rather than remaining an experimental technique limited to exceptional pilots. Her post-qualification interview revealed confidence levels and situational awareness that exceeded typical new pilot performance using standard training methods. The power control technique eliminates the constant instrument monitoring that traditional approaches require, she reported, allowing complete focus on visual cues and deck motion that determine landing success under operational conditions. The breakthrough demonstration that would validate Walsh's technique for fleet adoption was scheduled for October 12th aboard USS Forrestal, where senior officers from Naval Air Systems Command would observe comparative testing under operational conditions that simulated combat deployments. The test protocol required multiple pilots to execute both traditional and power control approaches during identical sea states and weather conditions, creating direct performance comparisons that would determine official Navy position on technique modification. Rear Admiral James Mitchell, commander of Naval Air Force Atlantic, had agreed to observe the demonstration despite personal skepticism about experimental landing techniques that challenged established training doctrine. Mitchell's combat experience during World War II and Korea had taught him to respect innovations that improved operational effectiveness, but his administrative responsibilities demanded careful evaluation of changes that might affect pilot safety across the entire naval aviation community. The demonstration would determine whether Walsh's technique merited fleet-wide adoption or represented dangerous experimentation that threatened systematic training standards. The morning weather briefing painted conditions that would test both landing techniques under challenging but representative operational scenarios. 15-knot winds with gusts to 25, combined with 8-foot seas that created significant deck motion, would simulate the marginal conditions where most carrier landing accidents occurred. Traditional approaches had historically shown degraded performance under these circumstances, with accident rates climbing dramatically as environmental conditions exceeded optimal parameters for speed control methods. Walsh briefed the demonstration protocol to assembled test pilots, emphasizing that safety considerations required conservative execution despite competitive pressures to prove technique superiority. Each pilot would execute 3 approaches using traditional methods, followed by 3 approaches using power control techniques, with landing accuracy and pilot workload, assessed through both objective measurements and subjective evaluation. The demonstration would provide definitive data about technique effectiveness while maintaining operational safety standards that protected personnel and equipment during evaluation phases. Lieutenant Commander Rodriguez volunteered to fly first, his experience with both techniques making him ideal for establishing baseline performance standards that other test pilots could reference during their own approaches. His reputation for precise flying and analytical thinking provided credibility that would influence how senior observers interpreted demonstration results. Rodriguez understood that his performance would determine whether Walsh's revolutionary technique received serious consideration or was dismissed as experimental curiosity unsuited for fleet operations. The first traditional approach proceeded according to textbook parameters, as Rodriguez maintained 135 knots throughout the pattern, despite gusting winds that required constant power corrections to hold airspeed within acceptable limits. His workload was immediately apparent to observers as continuous throttle adjustments competed with visual approach monitoring for attention during critical approach phases. The touchdown engaged the number 4 wire, acceptable but not optimal, with deceleration characteristics that indicated marginal energy management during final approach segments. Rodriguez's first power control approach demonstrated immediate differences in pilot workload and aircraft response, as he allowed airspeed to vary naturally while using power changes to control descent path directly. The technique appeared chaotic to observers expecting mechanical precision, but the aircraft's flight path remained remarkably stable despite speed variations that would have caused concern using traditional methods. The touchdown was precise, engaging the number 2 wire with authority that suggested superior energy management throughout the approach evolution. The comparison continued throughout the morning as additional test pilots confirmed Rodriguez's initial results under identical environmental conditions. Traditional approaches showed characteristic patterns of increasing pilot workload and decreasing accuracy as wind gusts and deck motion challenged speed control capabilities. Power control approaches maintained consistent performance across varying conditions, demonstrating adaptability advantages that translated into measurably superior safety margins during marginal weather operations. Admiral Mitchell observed each approach from the landing signal officer platform, his expression revealing growing comprehension of technique differences that challenged his assumptions about proper carrier landing methods. 30 years of naval aviation experience had conditioned him to recognize superior flying when he witnessed it, regardless of whether techniques conform to established doctrine. The power control approaches demonstrated aircraft control that appeared more natural and responsive than traditional methods, suggesting fundamental advantages that merited serious consideration despite institutional resistance to change. The afternoon testing session would include night approaches under artificial lighting conditions that simulated combat operations where visibility was limitations, created additional challenges for traditional landing techniques. Night carrier operations historically produced accident rates double those of daylight operations because reduced visual cues made precise speed control more difficult, while deck motion remained equally challenging. Walsh's technique promised advantages that might prove even more significant under conditions where pilot workload reduction could determine mission success or catastrophic failure. As darkness settled over the Atlantic, USS Forrestal's flight deck transformed into a surreal landscape of colored lights and mechanical precision that would challenge every assumption about night carrier operations. Red lighting preserved pilot night vision while yellow sodium floods illuminated the landing area in harsh geometric patterns that created optical illusions for aviators approaching at 130 knots through blackness, broken only by the ship's wake phosphorescence. Walsh understood that night operations would provide the ultimate test of his power control technique, where reduced visual references forced pilots to rely entirely on instrument data and landing signal officer guidance. Lieutenant Commander Patricia Hayes, the Navy's first female test pilot qualified for carrier operations, had volunteered for the night demonstration despite having only 47 night carrier landings in her logbook. Her engineering background from Stanford provided analytical skills needed to evaluate technique differences objectively, while her recent qualification meant she possessed limited experience with traditional methods that might bias her assessment. Hayes represented the future of naval aviation, where technical competence mattered more than institutional tradition in determining pilot assignments. The first night approach using traditional technique revealed immediately how darkness amplified every challenge that daylight operations had masked. Hayes fought to maintain precise airspeed control while simultaneously processing landing signal officer corrections, deck motion cues, and instrument readings that competed for attention during critical approach phases. Her workload was visibly overwhelming as multiple information sources demanded processing speed that exceeded human cognitive limitations under stress conditions. The touchdown was successful, but required aggressive last-second power corrections that indicated marginal energy management throughout the approach evolution. Hayes's power control approach demonstrated remarkable differences in pilot capability when freed from rigid speed maintenance requirements during night operations. The technique allowed natural focus on visual cues and landing signal officer guidance rather than instrument monitoring that divided attention during precisely the moments when external awareness was most critical. Her voice remained calm throughout the approach, indicating reduced stress levels that translated into better decision-making during the challenging final approach phase where night carrier accidents typically occurred. The landing was precise beyond anything observers had witnessed during previous night demonstrations, engaging the number 2 wire with authority that suggested superior spatial awareness despite limited visual references. Hayes taxied clear and immediately requested permission for additional approaches using the power control method, her enthusiasm indicating pilot confidence that rarely characterized night carrier operations among newly qualified aviators. "The technique feels natural once you understand energy relationships," she reported over the radio, her voice carrying conviction that impressed senior officers who had expected experimental methods to prove inadequate under challenging conditions. Commander Jake Thompson found his resistance to Walsh's technique crumbling as accumulated evidence challenged every assumption about proper landing methods that 3 decades of experience had validated. The landing signal officer's credibility depended on maintaining safety standards, but the demonstration results suggested that traditional techniques might actually be creating hazards rather than preventing them. Thompson had guided thousands of successful recoveries using conventional methods, yet Walsh's approach produced consistently superior results across all test conditions, without requiring exceptional pilot skills or ideal environmental circumstances. Admiral Mitchell called for a brief conference in Forrestal's flag briefing room as the night demonstration concluded, gathering senior officers whose decisions would determine whether Walsh's revolutionary technique received official Navy endorsement or remained experimental curiosity. The assembled leadership represented institutional knowledge spanning 4 decades of carrier operations, but their collective experience was being challenged by mathematical evidence that contradicted fundamental assumptions about aircraft control during landing operations. By January 1955, Walsh's power control technique had been quietly integrated into Naval Flight Training Command curricula at Pensacola, where accident rates during carrier qualification dropped by 83% within 6 months of implementation. The stubborn MIT engineer who trusted mathematics over conventional wisdom had transformed naval aviation through 3 aluminum blades spinning at the edge of impossibility, proving that sometimes the most dangerous idea in military aviation isn't trying something new, but continuing to do what everyone knows is right until the numbers prove it's killing people.